Hello, everybody, and welcome in. We are so excited that you are joining us today. We have an amazing demo in store for you. We're just going to give everybody about 2 minutes to filter in and get situated. So now is a good time to grab some water, coffee, whatever you're needing, and we will get going in about 2 minutes. Thanks for your patience. If you are just entering the meeting, we're just going to give it one more minute to make sure we can get everybody in. So just one more minute. Thanks for your patience. Looks like we are ready to rock and roll. Thank you again, everyone, for joining us. We're really thrilled that you're here. If you have any questions during the webinar, there's a question box on the side. Feel free to type it in there and we'll get that question answered for you. But please enjoy our demo. And at this point, I'm going to turn it over to our presenters.
Hello, I'm Matthew Rakuski. I'm the product owner for Content Integrations. So today we'll be showing off basically attack graphs with this new stages. Along with me is Joe Udenfreud. He is also a PO here, and so I'll be starting off showing the Iranian attack graph, and then kind of how we're integrating all the stuff together, and then he will be showing another attack graph and how we're looking at using that in like a report out. So let's make sure I'm sharing my screen here. All right. Can't see if you guys are sharing. Are we able to see my screen on the right one?
Yes, all good there.
Okay, cool. All right, so previously we've had these attack graphs, and they can be pretty large and daunting if you look at it as a whole. I mean, this has, I believe, 28 stages to it. And when you're looking at an attack graph like this, there's a lot going on. There's, like I said, tons of steps. But what's actually going on? Because each individual step, you are trying to either prevent or detect something along the way, but each one by itself really doesn't mean much holistically to what you're actually trying to be stopping. So essentially, what we've done and we're able to do with these stages is we have these amazing in-depth research people on our adversary research team, and they have this whole context of a blog of what's going on in each step. But this doesn't relay over into the attack graphs until now, where we are able to group multiple steps together. And not only are we able to group these steps, which allow you to assign roles and which assets holistically, so you don't have to go into each individual step to assign those, but we're also able to add the context to it. So we will be naming the stages, or the stages, and then the description. Our attack graph begins with the initial exploitation of log show 4. So then from there, then we're also able to change which role we're looking at, essentially what's being a part of each of these stages. So in the whole process, you're now seeing not just, okay, well, we have add directory defender exclusion list. Okay, then you move on to download shell. What you're actually being able to get from that context is we're starting off assuming that log4 shell has been was used to gain access. And then we are now looking at across this whole stage of saying, okay, they are trying to add an exclusion so that the actor is not having that scanned in the whole C drive. Then they're dropping their malware, the crypto miner, and they continually move on through that process. So it's able to make it a little bit easier. And then you can always add extra stages yourself if you're doing these. But again, like I said, just a simple create steps. But from there, we're able to move on to the next phase, discovering persistence. And like I said, in each of these phases, stages, sorry, there is a description that we'll be adding. And these will be added by our adversary research team for every single attack graph going forward from once we release these. And then we will also be going back as it may take time, but we'll be going back and adding them. So it helps everyone to understand. So I guess context is the magic word of the day, essentially. But yeah, so we're looking at discovery and persistence. So the actors extracting files, looking up an IP to check to see if they actually have where you are. Then they're scheduling persistence tasks. Moving on to the C2 and keylogger stage, they check to make sure that they can actually connect to the, here, maybe zoom in a little bit more for people, connect to 888, Google DNS. Then they run the system scripts, discovery processes, and download Mimikatz. So pretty straightforward. Each of those, I don't know how much knowledge people have in threat research in general, but then at least if you don't know these, you can go in. Again, when the scheduled task is executed, the binary will decode additional PowerShell codes, and it has. One of the first expansions we're going to be doing is expanding this description so it's easier to see, because we know there is a lot of information in each of those. But essentially, move on to the next phase, and the credential harvesting, lateral movement, and cleanup. Pretty straightforward of a description. We see that Mimikatz is the keylogger, dumps those passwords, and then they try to move laterally. And again, after succeeding executing their malware, the actor begins to move laterally. And so if you have any questions about what's actually going on, said it's simplistic in its design, but it also helps, I believe, for anyone to understand what's going on, no matter who's looking at this. But then we have the branch off of where the actor is then, once they've discovered an asset, comes to this side of it. And as we were talking about before, we have these roles, and this is a different asset assigned to the laterally discovered target role. And that allows us to, so if we look at roles, it allows us to edit these and give a description for what that role is for that whole stage, and assign what the actual machine that we're looking for. So you can add tags and stuff. And then the goal of this will be to help to also minimize which assets that you're actually looking at by filtering them down to, like, if this is going to be a Windows specific scenario, that you'll only see Windows based assets. But so then you'd pick the asset you're looking at, and you just quickly assign it, and then it would assign it to all of that whole stage. But essentially, once we move to this side of the attack graph, we are looking at a new asset, but the threat actor does pretty much the exact same thing. They discover, drop mining, do the obfuscation, go on to the next attack stage, and they are installing the miner, and then they do the file persistence, essentially, which this all leads back to the final stage of account manipulation, where the actor will use privilege escalation to create a new account. and making sure that if their initial accounts disappear, that they actually still have another account that they can retain foothold on the box. So I know I sometimes speak a little quickly, so if anyone has any questions before I hand off to Joe, please let me know. I'll be glad to answer anything. Okay. Let's give Joe the ball.
All right, I'm here.
There you go, Joe.
Thank you, Matt. Okay. Everybody should see my window, hopefully. Okay, so I'm here to talk about why did we do this, and I'm also going to close with another example of a multi-test point attack graph with lateral movement and stages as Matt just presented. So I'm going to close with another example. But before I do that, I want to get into a little bit of why we did this. You know, and kind of give you a little bit of a bird's eye view of some of the things that have been going on in the research and development branch of Attack IQ. So when we started with Atomic, and Atomic is still there and Atomic is still valuable, but it's very unit test heavy. So what I'm going to show you and what I want you to take away from this is that we've expanded and we've evolved over time from individual unit tests meant to understand whether or not a security control is there. It's sort of a tap, tap, are you listening kind of thing, because you want to understand if the security control is present before you launch a full-scale attack. But we've evolved from that all the way into what Matt just presented to you, which was really essentially a campaign, right? So there's a very big difference, and please allow me to explain. So when you run scenarios atomically, what happens is this: if everybody's familiar with the system utilities on a Mac or the system utilities on a Windows machine, essentially what's happening is you look at all of the different services that are running, and we're no different, right? So we're a service that's running. This is our agent process that's running, and every single time we introduce a new scenario in an atomic fashion, what we do is we introduce a new process along that tree, right? This is our agent running. This is the process that spawns when you run an atomic or an attack graph. And then atomic, when we're in the atomic world, right, or in the atomic type of assessment, we're going to do a single behavior. We're do no harm, so we're going to clean that up. Right now, it could be something. Behaviors are just that; they're just behaviors, right? So it can be something as, you know, as innocent as modifying a registry key, or it could be something, you know, as dangerous as downloading a malicious file. Whatever it is, the idea is that when you run these things in isolation atomically, that's really not true attacker emulation, right? It is good for detecting how granular you're able to respond and detect behaviors, right? But very often there's this balance between security and availability, right? So you don't want to stop every single time a registry, or even detect every single time a registry key is modified. What you'll end up having is a million false positives, right? It happens every single time you install a piece of software on a Windows machine. So you don't want to have to detect an alert on that. What you do want, right, is you want to have an understanding of whether or not your security controls, in this case, your EDR, is listening. And you want to, but you also want the ability to chain these behaviors together to really make it look like adversary behavior. So let me continue. This is what we started with: single process, single scenario. We clean it up, we tell you prevented, detected, we spin it down. We spin a new process with a new process ID, and then we try another scenario. Again, good, atomic, unit test heavy, right? And we needed to evolve this so that we can give you a more realistic breach and attack simulation. So what we moved to a couple years ago with the first version of an attack graph is this. We introduced logic, so the little mini attack graphs that you see are very similar, right? So we have the agent, and then we have the service that spawns off of the agent. And now we started to chain these behaviors together so that we could trigger the EDR control, right? That has a threshold of, hey, I'm seeing behaviors, but where does it, you know, where does behavior go from normal behavior to something that we may want to either prevent or alert on, or send somebody to go and triage and see what's happening? Well, in order to do that, we need to have logic. A threat actor has the ability to introduce this type of logic, if then else, right? If scenario one was prevented, maybe I want to stop the attack graph, but maybe I want to try something else. before I move on or before I say, hey, this is an actual prevention. And I'm going to show you an example of that. But we were very successful in triggering the detection and response capability of some of the major EDR vendors, right? Previously, if you're running individual behaviors and saying that you're emulating a threat actor, that's not going to trigger a response atomically, right? You have to chain these behaviors together to trip the threshold of the AI ML-based EDR control. But as the world moved on from EDR to XDR and really understanding that it's not one machine in isolation that you have to stop, it's actually spreading and lateral movement. And the point of this call is really to demonstrate how we've moved on and evolved into multi-test point. And what does multi-test point means? It means we're not going to be doing the same thing in carbon copy over and over again on individual machines. We certainly can do that. We're not taking that away. But what we're going to do is we're going to emulate a realistic attack by giving you different behaviors on different machines in a coordinated fashion. So let me continue. Some other things that we improved upon along the way is the ability to become adaptive with variable passing. So previously, the if-then-else logic is nice, but a real attacker is going to learn along the way, right? So what does that mean? That means this is a variable passing attack graph. So essentially, what we're going to have to do is, if we want to modify a registry key, and the next scenario is to call a registry key, you want it to be the same registry key that was modified, because that's how a real attacker would work, right? If in that registry key it says invoke a new command called command or a new process called command.exe, the rest of the attack should run from command.exe. Same thing here. It's a little easier to see. If scenario 4 is to find some sort of personally identifiable information file, then scenario 5 is to compress those files. It should be the same files, and it should be this, and furthermore, it should be the same files that are exfiltrated, that were compressed, that were initially found, right? This is how we become adaptive. This is how we become realistic. And where are we going with this? Lateral movement. Same thing holds. If the attack graph dictates that we want to start by finding initial access or downloading a malicious file, and then we want to dump credentials and then do some form of network discovery, whatever credentials were found here, and then whatever IP and ports that were found listing here, that information can now be used in order to move laterally. And that's what a multi-test point attack graph is, right? That's where we start to cross the chasm from atomic and atomic attack graphs, or I shouldn't say atomic attack graphs, I should say atomic scenario execution, and then attack graphs, which are a series of behaviors being executed multiple times on different machines, right? So it's the same behavior or the same pattern of behaviors on many different machines versus a particular pattern of behavior on one machine, and then potentially different behavior or patterns of behavior on other machines separated by time, which is really moving towards a campaign, right? And also, again, using the information we discovered along the way so that we can become more realistic. We're not going to blindly move to something that wouldn't have been identifiable on the system where the initial access took place. So lastly, we're going to talk about a campaign, and this is what I mean by different things, and this is the true nature of a multi-test point attack graph. It means we can start the attack on one or more machines, but then at some point, at a different time, we're going to start with different behaviors on different machines. And this is really more emulative of an attacker campaign. And let me show you what I mean. And I'm going to show you a couple of different things and kind of give you a preview of some things that are already available, and a preview of how we're thinking about going forward and building. So, okay, these are what we think of as attack graph snippets. These are behaviors or chains of behaviors that can be reused. Why are we doing this? Well, a lot of what you see for the e-crime groups out there and what they're doing, they're using different combinations of access and malware distribution and different types of ransomware. So it's the same thing over and over again, but in different combinations in use by different crime groups. And there's definitely, you're going to see more research, and I'll leave the detailed explanation of that to our adversary research team. But there are a lot of, the brain power driving this. So what's cool about these things, right? You're going to see it over and over again. You're going to see credential dumping, network discovery, and some form of lateral movement, because that's how we spread across a network. And what you'll see with the multi-test point attack graph, and specifically with the stages, as Matt showed before, is that you'll get an understanding very quickly of how bad the problem is. If I can get initial access on a single machine, but I can't move laterally, okay, the problem isn't that bad. If I can get initial access on a single machine and I can move laterally, okay, that's a little more scary. But then we'll move on to the ransomware process. So it's, if I can get initial access and I'm isolated, maybe I can encrypt, maybe I can encrypt. Okay, we want to start looking at that as a severity. If I can get initial access and I can't move laterally, your problem is somewhat isolated. But if I can move laterally and I can encrypt, you know you have a big problem. That's a severity 1 for sure. So let me show you a little bit about variable passing and lateral movements in these snippets. And then finally, I'm going to close with another multi-test point attack graph ransomware example with stages. So here's an example of one of those snippets that you just saw. What you're seeing here, this is results, right? This is open ports checker, dump Windows passwords, lateral movement through remote desktop protocol, and then command execution. Now, I've configured this attack graph to pass variables. Passing variables means that when we run open ports checker, whatever is discovered there is then going to be pushed forward to be used in a later step. So what's going to happen is this series of steps you'll see here runs on one machine. And then if we're not prevented, and we were not prevented here, the next step, right? 1, 2, 3 scenarios are running on unprotected 2016 CTP. The next one is going to be running on this one, LM, right? So it's a different machine. And this is really, you know, it's probably 2 months old already or 3 months old, but this is the first time for us that we've been able to move laterally to a different machine and perform a different behavior in the same attack, right? Previously, we were running exactly the same behaviors, either atomically or in an attack graph on many machines, right? Here, we're starting on one machine and we're doing some things, and then we're moving to a different machine and doing some other things. And we can add on to that, right? This is meant to be a pretty simple example. So let's see what happens. If you look down here at the results, what you see here is open ports checker. It wasn't prevented. Let's take a look at the details. So detailed findings, it found 172.31.5.185 listing on 3389. If I look at the activity details, you see this really nice bit here. It's adding that information to context. That means it's going to use the information that was discovered using open ports checker at a later phase of the attack, right? Again, becoming adaptive the same way an attacker would. An attacker has to use this technique of open ports checker to see what's listening around it in order to facilitate lateral movement. If it can't, it's not going to move to what it can't see. Okay, next step down is dump Windows passwords. Very common technique. We're going to dump Windows passwords. We're going to see if there's anything there. Here are the detailed findings. It found a whole bunch of passwords. So I now have a combination of an IP address and a port that I know is listening, and then some credentials with which to use to attempt to move laterally. And again, if I look at the activity details, what you'll see is we're adding that information to context. In this particular case, we took 2, right? But we can ratchet that up or we can ratchet that down. We can try in as many different combinations as you have the appetite for. So if we wanted to try to move laterally with every single one of those combination of user and passwords, we certainly could do that. In this case, we're only using 2, just for simplicity and demo sake. Next step is to actually take the information that we learned from the first 2 phases and then use it to move laterally. So here's lateral movement through remote desktop. You can see here it's running on this machine CTP. And what you're going to see is 2 different attempts at lateral movement. The first one was prevented. So the first one, if we look at the activity details, we attempted to move laterally to this machine that was discovered using this credential, and we were prevented. Next one, not so lucky. So we tried to move laterally to the same machine, but we used a different combination of user ID and password, and this time we were successful. And because we were successful, we were able to conduct the next step, which is command execution on a completely separate machine. And this is what I mean by a multi-test point attack graph. For the first time here, we're actually conducting different scenarios on different machines as part of the same coordinated attack. And this could be as complex or as simple as this. This is a 4-step attack graph. What you're going to see going forward are things like we're going to dump credentials inside of a cloud, inside of a host that lives inside of a cloud, AWS or Azure. And then we're going to use those credentials from an external entity to try to pull down information maybe from an S3 bucket from a place that's not inside of that same cloud to see whether or not that trips an alert. There's a lot of utility to multi-test point attack graphs. Just being able to, one, share information that was discovered along the way and become adaptive the same way an attacker would, and also be able to execute a different series of behaviors or even the same series of behaviors on a different machine as part of a coordinated attack pattern. So with that, I'm going to show you the last example, which is going to go back to very similar to what Matt showed. So here we have our response. And again, these smart folks over here on our adversarial research team, this is where we actually get to leverage them and scale them so that we can distribute their information and the ability and their knowledge of attack and defense to all of our customers, right? They've put together all of this research on Hive ransomware. This happens to be one. There are responses. This is a US CERT alert. We respond within 24 hours to every single US CERT alert. And we want to really make threat intel actionable. That's the name of the game here, right? So in order to do that, we need to take our response and we need to give our customers something that's actionable, something that they can actually learn from. And that's what we've done. So I'll leave the blog reading to you guys. All of this is available on our website, but I'm going to show you what we did with it. And this is going back to what Matt said. We have these stages, and each stage is a series of behaviors with an intention, right? It's one thing, and going back to the atomic example, to run a singular TTP. That's very good if you already know all of the information that's embedded in the attack graph here. But if you don't, here's what we're going to show. So again, all of our attack graphs, whether it's single or multi-test point, are going to have this new concept of stages. All of the stages are really going to say, what is the adversary trying to accomplish with these series of steps? The other thing that Matt touched on was they're going to come with roles. What role or what type of machine should you assign to the individual stages of this attack graph? So similar to what you saw.
Yep, Joe, we have a question.
Oh, sure.
Is the relative value of an asset somehow included in the network profile? If not, how can that be added?
Great question. So the relative value is really something that's going to be subjective from company to company. If you know the relative value, you can add something here like, because you're going to pick the asset itself, right? The adversarial research team is going to tell you what type of role you want to play, but you can put in high criticality, low criticality, medium criticality. A different feature for a different day is how do we, especially for large deployment on a customer network, how do we add context of the value of assets from a third-party source? So let's say something like ingestion of data from Qualys or Tenable, and the understanding that comes with which, let's say we were able to hook into Qualys, which we can, by the way, or Tenable, and add that metadata to an asset to then be used in the selection of an asset, right? That's how we would do it. Today in this example, right, if I wanted to say high criticality, because I know I'm about to pick an asset that is high criticality, I can do so. But another demo for another day is how we're going to ingest data from third-party sources, whether it's a vuln scanner or some form of CMDB, so that we add additional context to the assets. That's a demo for a different day, but that's in the works as well. Does that answer the question?
I think it does, and since we're already kind of pausing for questions, we have a couple more here.
Please.
Let's see. How do we add assets that are not found in the firewall rules, such as a SCADA item and circuit breaker status downstream of the SCADA?
Today, when you say assets that aren't found in the firewall rules, so this is only going to, the thing about a multi-test point attack graph and the ability to continue on a separate asset is that you need by nature to have an agent installed there. Again, another demo for another day is agentless, and the ability to distribute a package to a place where there is no agent. That's a roadmap item. That is something that we're actively developing, but not quite ready yet for demo.
I don't think we'll be installing on SCADA either way.
Right, right. So, again, we'd have to talk about that. I mean, whoever asked that question, I would love to double back and maybe we can talk about the use case. But yeah, the idea behind this is we want to put guardrails around it such that let's say we did find a very wide open system. How many different places would you really want to discover and move laterally to before you realize, 1, 5, 10? Again, that's going to be up to the user. But today, with a multi-test point attack graph, you cannot continue on in a place where there is no agent installed. So all of this is going to be agent-based for now, but I'm happy to double back and take more questions around that because I do recognize that there are certainly places that we want to conduct testing that maybe a persistent agent presence is not possible. And if it sounds like I've talked about that in a different meeting, I have. So I'm happy to schedule time for those interested or potentially put together a roadmap presentation or a presentation specifically around dissolvable agent or agentless.
Yep, and last question that's currently on here, it's pretty similar. Sounds like the controls associated with the assets and other nodes and the network are automatically included, I assume from the firewall rules.
So the controls, when we say controls, the controls that we have here, I need a little more information on that question. We know about the presence of controls, and obviously, Matt, it's something you're very familiar with because you manage content integration. So different feature of the platform. When we hook into your security controls via integrations, and we do this for the purpose of when we run a scenario, we will tell you via agent server telemetry whether or not that behavior is prevented or not prevented. But then through integrations, and hopefully most folks are familiar with our integrations, after we get this determination, it's very valuable to understand whether or not the security control, let's say in this case an EDR or a firewall, actually detected the activity that we introduced. So we then send a query with logic that looks like, hey, at 10 a.m. on Joe's laptop, I introduced a scenario, dump credentials via Mimikatz. Let's go and look. Hopefully it was prevented. Let's see if we can give attribution to whatever security control actually prevented that behavior. Well, the only way to do that is actually to hook in via API, which is the whole purpose of our integrations. And then we'll send a query that says at 10 a.m. on Joe's laptop, did you see a behavior that looked like some form of an IOC? We'll send that query, we'll pull back. Hopefully it's a yes. Okay, in this case, Microsoft Defender for Endpoint or CrowdStrike or Cylance or whatever your EDR saw that behavior. We can give attribution. It was detected by that control. It was prevented according to our telemetry. You're getting value out of your EDR solution or your firewall or whatever it is. So we hook into integrations that way. We know of the presence of EDR because before we ever send a query, when we first set up that integration, we can then query the database of the EDR to say, hey, do we have matches with the known assets that we have in the Attack IQ database? And then we can give attribution. Yes, we believe CrowdStrike is present on this endpoint. Yes, we believe Cylance. We can't quite do the same thing with network controls because it's a little bit more complex. However, we do have a topology, and in most cases, if we only have, let's say, one integration for one firewall, or if we know every time we run a network, some sort of network behavior, we expect that to be picked up by Palo Alto. We can query Palo Alto every single time, or Cisco, or whatever the vendor, Fortinet, whatever the vendor is you're looking to assume. So we don't always know, right? But through integrations, we have a pretty good idea of where the customer wants us to look for different types of behaviors. And I'll follow that on with each scenario is tagged with, let's see, I'm going to zoom in on this in a minute. But each scenario comes with tags where we talk about, and of course it's not actually here, I'd have to go back, but they come with tags, and those tags drive our integration queries. So disable Windows Defender via registry key, we know this is an EDR. If we were to go back and look, we can see that it's an EDR. So whenever we run this behavior, when we go to look for detections via integration, we're going to route it to an EDR. And the same thing would be true of, let's say, lateral movement or a call to any bad website, right? That's going to be something that you want to route to a firewall for a detection query. Any questions there? Any other questions? Okay, well, let me go ahead and show the final attack graph here. So this is our attack graph with stages, and it's also a multi-test point. Same as what Matt showed you. There's a lot of stuff going on here. There's 1, 2, 3, 4 stages, right? Stage 1, 2, and 3, and I promise I'm going to dive a little bit deeper in here. I know we're getting towards, a little further towards the second half of the hour, but I'm going to go into detail a little bit about each and every one of these stages. Again, when we produce things from now on, it's going to come with guidance from our adversary research team as to what type of roles you should assign in order to perform these behaviors or this attack in the most realistic type of fashion. So let me get into it again. Stages and roles, you'll assign the roles first so that those roles can be assigned to a stage. So for example, if a particular set of behaviors requires let's say an Active Directory server, or a place with a logged in user, or a place with an external hard drive, or any number of different things that a scenario might require to run without error, that information is going to be here, right? We're talking about the assumptions that we're making as the attacker. We're playing the bad guy here. Remember, Attack IQ's motto is think bad, do good, right? So let's get into what's going on inside of the attack graph. Okay. So initial access, defense evasion, persistence, exfiltration. That's what you're going to see here, right? I've kind of gone with the MITRE nomenclature. It's going to run on this machine. If I go into the details here of editing the stage, you can see here we select the role. This would have been done previously. As I mentioned, we're going to come with roles. We're going to assign assets to roles, and then we're going to use that. So we have logic here. Again, it's up to the user if they want to determine, do we want to call the stage not prevented if all the steps were prevented, if any of the steps are prevented? If you want to select individual steps, we can do that. And again, we have a description here, and this description is important because it describes what the series, or I should say the intention of the attacker, or the intention in this case of the threat researcher who put together this behavior. So you get to learn something here, and that's the idea, is we're pushing knowledge forward from those people on our adversary research team. What you see here is process discovery through task list, security software discovery, right? We're looking to see what's running on this machine. The assumption is this machine was compromised either by phishing, by spear phishing, somebody clicked on a bad link, somebody downloaded a bad file, or somebody popped a vulnerability on this machine, and now I have access. This is my first machine. This is my initial foothold as the attacker. First thing we're going to do as the attacker is we're going to see what's going on. So once we understand what's going on, we're looking for specific security software, and we're going to try to disable Windows Defender via registry key using Windows API, right? So I'm looking around, I'm looking to see what's going on, right? I'm doing some reconnaissance here. Then I'm looking to disable your security, right? I'm looking to make sure that I don't get caught. That is defense evasion. Then I'm going to look to establish persistence. I want to be able to access this machine anytime I want. A great way to do that is to create an account that nobody knows about except me as the attacker, right? If I can accomplish that, then I'm going to look for files. Then I'm going to steal them. I'm playing the attacker here, right? This is how the Hive ransomware groups work when they initially when they initially get on a machine. Now, the thing about this stage and the series of steps, as I mentioned, what the e-crime groups are doing is that they have reusable steps. They've commoditized malware, they've commoditized distribution, and they've commoditized the ability to encrypt, right? So they're using different combinations of these patterns. And again, the illusion is that, what I'm alluding to here is that very soon you're going to see these combinations in a library so that you can build your own if you choose to. And our adversary research team is going to be reusing a lot of the same steps and different combinations and patterns to emulate different ransomware groups that utilize these commoditized tools. Okay, so as I've shown you the first step here, if I'm successful at these things, the next thing I'm going to look to do, again, is lateral movement. And again, these are very common techniques. If we want, the idea is if you can get in on one machine, fine. If you're isolated and you can't move laterally, your problem is not that big, right? But if you can, and that's what we're looking to determine here, is we're going to, if I click into the stage here, after the data has been harvested from the original point of compromise, now I'm going to look to see what other additional damage I can do, again, playing the role of the attacker. I'm going to scan for remote systems. If I can find some systems, then I'm going to attempt to move laterally. And what you see here is 1, 2, 3 different methods of using that discovered information and 3 different ways or attempts to move laterally. If I'm stopped here, if I'm successful here, well, I don't have to do these 2 next steps. If I'm not prevented, guess what? I'm going to go and then try to reuse that same series of steps from the first stage on an additional system. So if this looks very similar, right, it should, because it was also the first stage. The difference is it's the first stage of the attack rerun on a machine that was discovered from the second stage on their initial access point. And the idea around this is just what I said before. If I can't move laterally, if I can't discover systems, then my problem is isolated. If I can move laterally and I can discover a lot of additional systems, you want to start treating that as a very serious finding, right? This is a very good use case for proper access control list, proper network segmentation. This is how malware spreads. This is how this is how problems start. And again, you can imagine when you have an attacker with an intent to encrypt and hold you for ransom, the more systems they encrypt, the worse your problem is, right? So you want to really identify, and that's the beauty of stages. We can tell you how big the problem is by giving context to all the individual behaviors that are going on there, right? This is a big change from what we've done previously. Okay.
Yep.
And
Since we're coming up on like 4 minutes left here, Joe, do you want to kind of jump to the report out that you were talking about?
yeah, I'm gonna. I think it's up to 11, but yeah, I'm gonna wrap it up really quick. So the last phase, and sorry, yeah, I'm just gonna show this one real quick, Matt, because this is the impact phase, right? So this is where we get to talk about a job runs, we download the ransomware, we then save the ransomware to disk. We want to see if these things are possible. Again, this is going back to the first machine, but you'll have an understanding of what the actual impact might be depending on how many systems are discovered and available to move laterally to, right? So you want to really understand. So again, problem is isolated, fine, you can't move laterally, but you can encrypt. Okay, that's a little more severe than if you weren't able to encrypt. If this stage is stopped, then you're in pretty good shape. But if the problem is not isolated and you can do these things, you really have a big problem. And that's what we're trying to gauge with a multi-test point attack graph with lateral movement and encryption. So I am going to close off and leave time for any questions. But at the end of the day, we're going to give you a report, or we're going to have the ability to give you a report that looks like this. You can talk about who. Well, we assessed who you are. Why? Well, you see here that the Cybersecurity Infrastructure Security Agency published a joint security advisory, right? We're going to respond to every single one. That's why you're going to conduct this testing. The what? That's our version or our response to that. And then we can give you a breakdown with a table of contents, and this is starting to look more like a traditional pen test report. We can talk about what we selected or what the scope was, right? What particular endpoints on our systems we selected and why. We can fill that in, right? Each network is unique, and we're not necessarily going to be able to tell you why you selected those assets to play the roles, but we can give guidance and all that sort of thing. And then you're going to see all of the information that you see in stages. Why do these things matter, right? And that's all coming from our threat research team, and they're going to give you all that information. That's why we conducted these series of scenarios. We'll give you what the outcome was, either via our prevention determination or third party via integrations, and we could start going through and really assessing if a realistic attack would take place similar to what CISA is warning you about. What would the damage be on your system? Determining that and how quickly you need to respond based on our testing is really what we're after here. So with that, I want to say thank you. Thank you for listening. We're very proud of the features that we're producing. The snippets that you see here that I showed, these are already available. The stages and the stuff that Matt and I showed, starting with the Iranian ransomware response that Matt showed, and the Hive ransomware response that I showed, snippets in every single attack graph, whether it be single or multi-test point, those are going to be available at the end of this month. So you should start seeing those in July. And from that point going forward, every single attack graph will have stages, and eventually we'll have a library of those individual stages that can be reused in different combinations to mimic different threat actors and e-crime groups. With that, I'll take any other questions and say thank you.
So it looks like we have one last question here. By stages, do you mean kill chain? And by roles, do you mean MITRE attack techniques and tactics and techniques? I would say no. The stages is more just aligned to like what's the intent. I think there will be a lot of alignment to kill chains, but as you could see in some of them, there was persistence and lateral movement in one. So it's whatever the whole intent of that stage is, but I could see why you would think that it's aligned directly to kill chain. And then from the roles perspective, that's more of like the user and like what asset is being used within that stage itself. But feel free, Joe, to
Yeah, no,
add any context.
Yeah, totally right. So MITRE ATT&CK, when we look at it, it's a catalog of different types of behaviors, but what we're kind of emphasizing here is that those different behaviors by themselves lack context in terms of attackers use different combinations and patterns of those behaviors. So those in and of themselves in isolation don't really tell you the story you need to understand without the stages, right? The stages are really meant to show how would an attacker utilize these behaviors that are cataloged with an intention, right? So the intention is to steal data or to discover something and move laterally. So it's combination, and it's going toward. I also understand the question of why it looks like kill chain, and it's yeah, I mean it's very similar, right? We're going to show you the art of the possible and where you're cutting it off. So there's a kill chain aspect there. The roles, on the other hand, right? The roles are meant to give guidance in terms of what the scenarios require to execute, right? An attacker is going to be looking for systems with different things depending on their intention. So again, going back to if certain scenarios are meant to run on a domain controller versus versus a server versus just a workstation, right? We're going to give that information in the roles, right? So the roles are really meant to say, hey, for this particular stage, we require an asset that meets this criteria because that's what the attacker would be looking for, right? So the roles are really meant to give guidance so that we can make asset selection as easy as possible, but it should also match the intention of the attacker, right? If we're running a series of behaviors meant for a domain controller on a system that is not a domain controller, we're going to error out, right? Where they're not going to have the system resources that are expected, and we're not going to be able to manipulate or to run the scenarios as intended. Hopefully that helps.
Great. Thank you both so much. And thank you everyone who joined us today. Just want to mention finally, please subscribe to our adversary research team content on our website. It's a great source of information there. And then also sign up for Attack IQ Academy for more insight there as well. You can just go to academy.attackiq.com to sign up for free. And these are all great resources. So of course, please reach out to us if you have any follow-up questions. I'm always available to answer there as well. But again, thank you so much for joining us today, and we hope to see you next time. Thank you.